Okay, so we really have two goals for today. One is to address these, especially number 3, if you have any lingering questions. And the other is that I wish to do two types, to demonstrate two examples of problems that show up very frequently. One involves similar triangles, and the other involves trig functions. So, there it is. Which problem from last night's homework is most satisfying? Please discuss with your table and come up with a consensus answer here.
Every time like I read the question, I just started like writing down stuff on the paper. So I was writing down and then it was trying
I like 17.
Do you like it?
Yeah, because I was just like, I didn't want to do this. I thought.
So what are you saying?
Okay, this table. Which problem was most satisfying for you? Number 17. Why is that? Isn't that great? I call those problems looks hard is easy. And those are wonderful problems. How many of the rest of you thought number 17 was very satisfying? Yeah, good. Okay. You guys. Any others? 17 also. How about you guys?
We'd have to agree with 17.
Okay.
27.
27. Why is that?
Because it was long.
Because it was long.
It took a lot of thinking.
Took a lot of thinking. Yeah. I call those problems workouts. You know, you do them
I
and
do hate
what's that?
I do hate working out.
Well, yeah, right. So there's a certain kind of workout where you're done and you just go, oh, why did I do that? And there's a certain kind of workout where, you know the phrase good tired? You do something and you feel good tired, that's that. And you guys? 17. All right. Which one was the most difficult? 19? 19C. Also 27. 19. 17 was the most difficult. Okay. 27. And finally, the most important, you have lingering questions about related rates. Okay. Now could work. Just tell me what the question is, and then we can. See if you can put it into a concise form, and I'll come back to you. Any lingering questions? Questions? Yeah, I hear you. Good. Can anybody relate to what she's talking about? You are alone in the world. I see some heads nodding. And what do you guys do to help that process out? Are there some things that we can do to help keep from getting confused, to keep the head straight? Excellent. Right process, yeah. If you have a format for your process, that might help keep from getting confused. Also, the equations that we end up using fall into some basic categories.
Yeah, it's like when we were doing the one with like the chronicle like yesterday.
Yeah.
I just like when we started using like the volume formula for like the second part of it just like it lost.
Oh, okay. Just the amount of detail, the algebraic detail.
Yeah.
Yep. I totally know what you're talking about, and it happens at multiple levels, right? So, even now, as I'm reading through math, sometimes if it's like a couple page development, you get to a point 3/4 of the way through and you're like, where do we get? And so what I find that I need is some perspective. And what I will sometimes do is start at the top and talk my way through it a little bit, so that I have a big picture of where we're going with this. And he's exactly right. The process. So equation followed by substituting followed by derivative is the basic pattern, and you look for that. I don't know if that helps.
But usually it helps if you have small that messes up, and then if you write it on the top, if it goes to the bottom, you can go to the left and right, and that messes up too.
So which way do you write it so that it messes up the least?
You just put it over like one with the
So lining it up vertically instead of, yeah. I taught Mrs. Durant's son my first year here, my second year here, first, second, third year here. And I had him for trig pre-calc. It was a class of 2 because the school was just getting started at that time, and they only met up through sophomores, so there were 2 sophomores in trig pre-calc. And the first homework I got back from him, you know how some people work down the page and some people work across the page? His problems were in zones. It looked like a risk map, where you had one problem here and he had literally done an outline around it. And he did another problem in the middle of the page and circled that, another one here. And I said, all right, this is not going to work. I'm going to make you work down the page, and I made him work down the page. He hated it because it would cut against the grain. Right? Time passes. He graduates. He goes off to Virginia Tech. He comes back after his first year. He totally forgot the books. And in first year engineering, the fundamentals of engineering class, they have a specific format that all problems have to be done in. You must do your problem on graph paper. It must have a title here. It's really rigid. Comes back and says, guess what I learned? I said, what did you learn? He said, if you format the problem right, it practically solves itself. And I said, wow, that's a really good observation. And of course, that is exactly what I've been trying to teach him. So sometimes format gets in our way. And if the format is chaotic, it causes our thoughts to be chaotic. So just formatting it might be another thing. Keeping in mind the process and then formatting the work so that it helps you to keep your head straight.
Was he formatting it just in different zones?
He was formatting it, but in different zones. But it turns out that some formats work better than others for keeping your head straight. So, for example, with solving multiple equations and multiple variables, I have a specific format that I have developed for myself, because any other format I just dork up and make stupid mistakes with. Okay, any other lingering questions about related rates? You guys? Questions? Jesse came in, he was so proud of himself. Tell us why.
I understood the concept of related rates and stuff, so I couldn't sleep, so I said I might as well finish up the UC.
And you got a lot more done. All right, good job. Yeah. All right. Bethany, you figured out your question.
Draw a diagram.
Right.
And then, well, what they want from me. Just seeing that, that's why I can do the calculus part and understand how you want implicit differentiation, find the variable, making it two variables, they get all of that. It's just finding what they want that I don't know.
Okay. So I want to take that and I want to give you some vocabulary to articulate your question. What you're saying is that you can do the mechanics of the differentiation. Yep. But what you don't understand is, as you said, the concept. Another way is when I read the problem, I have trouble translating it in math. That's really it. So let's actually take one of our example problems that I wanted to do today, and I want to focus some special attention on how to translate this. So let's take a look here at number 29 on page 253. And what we have in number 29 on page 253 is a man that is 6 foot tall. This is my version of a stick figure. And he is walking at the rate of 5 feet per second toward a street light. And the street light is 16 feet above the ground. So maybe I'd better make my man a little bit shorter. And now they ask this important question: at what rate is his shadow changing is the length of his shadow changing when he is 10 feet from the base of the light. Okay? Now there's two things that we're going to learn from this problem. And the first is we're going to focus on Bethany's question, which is how do you translate from English into math? And then the second thing that we're going to learn from this problem is that this problem is a good example of the use of similar triangles to construct our equation. All of you have seen this. I think I was probably, 3 or 4 years old. I know I was 5 or less because we lived in Houston. And we're walking along on the sidewalk in our neighborhood, and there's a street light. And what I noticed is that my shadow is absolutely huge. And that was very mysterious to me. How can it be that my shadow is huge? So I talked with my dad about it. My dad gives me an explanation, et cetera, et cetera. How many of you remember noticing that when you were a kid, or maybe you've noticed it more recently, that your shadow changes lengths as you move under the influence of the light, right? And so, why does that happen? Well, it's a really simple matter. Your shadow is created when the light is blocked. And the light is coming from this street light up at the top here. And so where your head is where the shadow of your head is going to be projected, and where your feet are is where the shadow of your feet are going to be projected, and the result is that your shadow is now a stretched out version of yourself simply because of the projection of your head and your feet and every point in between, right? So your shadow is going to end up being much larger than yourself possibly. Now let's do some translating. First of all, we're going to go through and we're going to mark up our diagram. We're going to mark anything that is constant with a constant.
Is that black line in the middle just a light beam, or is that part?
It's just a light beam. That's exactly
Shouldn't
right.
the red line be extended across to make it one big triangle? The red line, horizontal.
Oh, great question. I will in just a second. I'll do a different color. Okay, where were we? So we're going to mark all of our constants with constants. The light is 16 feet. That's not changing. That gets a 16. The man is 6 feet. That better not be changing. That gets a 6. But the man is walking towards the street light, and they say that he's walking at a rate of 5 feet per second. Anything that is a rate, I'm going to translate as a derivative. And so this is the rate of change of what? It is the rate of change of his distance from the light post. And I'm going to call that distance something, and I like x for distance. And x is currently 10 according to the problem, so I'm going to mark that as 10. And the rate of change, therefore, is going to be dx dt. And I'm going to do a quick sign check. Is dx dt positive or negative? And I answer that according to whether x is increasing or decreasing. And in this particular case, x is decreasing because he's walking towards the light, so that dx dt will be negative 5 feet per second. Okay? So that's the translation of that. Yes, sir.
In this situation, could you also put it on the reference? If you put the reference curve on the person, would it still be negative?
Yes, because now the lamppost is coming towards him, and the distance of the lamppost is decreasing. Now we go to the problem. They ask, at what rate is the length of his shadow changing? First of all, rate means we're looking for a derivative. And it's the derivative of the length of his shadow. So I go back to my diagram and I ask myself, in my diagram, where is the length of his shadow? And it's clearly the segment in red right here. So I'm going to call that something, maybe S for shadow or L for length. And I don't currently know the value of S, so I may have to go back and figure that out in a second. But what I do know is that I'm looking for ds dt.
So which one's your person? Okay.
In the diagram, the person is the 6 foot tall
I can't show it.
stick figure, and the shadow is the projection of that person onto the ground from the light that is 6 feet behind. Okay? And now here is the big idea. You asked earlier, what is the concept? The concept is that I have one derivative, and I'm going to try to leverage that to find another derivative. I am relating rates to one another. So really the name of this section, related rates, is the concept. We're relating one rate to another rate. And to get there, we start with an equation, and then we differentiate with respect to time. That's the big picture. Okay? So now all we need is an equation. And so here, we're going to focus now on how we get that equation. What I notice in my picture, although it's sort of badly drawn, is that I have two triangles that are similar to one another. And by similar, what I mean is that they have the same angles, and therefore their sides are in proportion. The big triangle and the little triangle. And so if I write the proportions that correspond to them, I can say that for the big triangle, we have 16 here, and we have S plus X as the length of that side. And for the little triangle, we have the man, and we have just S, just like that. And so now I can write proportions. I can say that S is to 6, just like S plus X is to 16. And what I have now is an equation that relates S and X together. Good?
Well, I just wanted to know, like, because when I was doing it, I had 6 of S and 16.
Yeah, that's a great question. This is also a valid proportion that comes out of this. Which one is easier to work with? Well, in the end, I'm probably just going to end up cross-multiplying to clear my fractions here. But if I had to differentiate, I'd much rather differentiate one that has my variables in the top and constants in the bottom, so I could use constant multiple, as opposed to having to use quotient. So this one's slightly preferred. If I had this guy, if this were given to me, I would simply probably flip both sides to make it this one anyway. Okay. So now, let me do a little bit of algebra first by clearing the fractions, multiplying both sides by the common denominator of 6 times 16, so that I end up with 16s equals 6 times s plus x, or 6s plus 6x. And by doing this, I now have a much more tractable equation to work with. Subtract 6s from both sides, and get 10s is equal to 6 times x. Now I can go in two directions with this. One direction that I could go is to find the length of his shadow if I'm curious about it. But that's not really my goal here. My goal is not to find how long his shadow is. That might be an interesting question. But my goal is to find out how fast is the length of his shadow changing, right? And so the length of his shadow is going to be ds dt. I need a time derivative. And the time derivative here is particularly convenient. 10 ds dt equals 6 dx dt, and I have a value for dx dt, which is negative 5 feet per second. So the ds dt is equal to negative 3 feet per second. And we're done. So this is a really good example of a problem in which we use similar triangles to set up our equation. Kathy, did that help address your question? Good. For the rest of our time, I'd like to consider problems that involve angles. And in particular, I'm going to take a look at number 33. Which is another shadow problem, but now we're going to be interested in a slightly different rate. In number 33, we have a building, and our building is 80 feet. And what we're told is that the sun comes down from above, and it creates a shadow on the ground, and the shadow is currently 60 feet long. And we are told that the angle theta is increasing at a rate of 0.027 radians per second. I'll make sure I have that number right. Ah, no. Totally wrong. 0.27 degrees per minute. Much better. And now they ask, at what rate is the shadow length decreasing? So you can see that this problem is, in some ways, very similar to the last one, except that now our lamppost is, for all practical purposes, infinitely high. So I'm going to need a slightly different approach here. Before we begin answering the question, I'd like for all of you to mark up the diagram. with everything that can be marked out. Go. Okay, and how does your diagram go? Oh, there. There's your diagram. Think out loud, please. Think louder out loud. Well, so let's start with, do you understand the question? Okay. So, now, you're going to try to mark as many things as you can here. So, what can be marked? Oh, you don't have your book in front of you. That's your problem. So you definitely need your book so that you can see what other information is there. What do you see on the diagram that is not on our picture up here?
The height of the building.
The height of the building, we have that. That's a
Oh, there.
question. Is the height of the building a constant or a variable? It's a constant, so we're going to leave that as 80. Good. What else is in the diagram that we do not have yet?
And the length of the
The length of the shadow. Is that a constant or a variable?
curve.
Okay, so how should I mark that? X, but not just X. How should I mark that? Samantha, there's only one really good answer here. Exactly. We're going to mark it as X and give its value. That's how the marking is done. Okay? Good. Is there any other information that I have not yet put here? What you got?
You could say DA or DT equals 0.27.
Yeah, except since they use theta, we're going to call it theta.
Okay.
Yeah, d theta dt equals 0.27 degrees per minute. And then finally, we want to translate what are they looking for. So in mathematically, what are they looking for? dx dt. Exactly so. We're looking for dx dt. And so, Bethany, we've captured it. We have one rate. We're looking for another rate. Now that focuses our attention. All we need is an equation that relates those two. Yes?
Use tangent of theta equals 80 over 60.
That's exactly it. Except it's going to be 80 over x because x is changing. That's exactly it. So, here's a big concept. What we have are lengths. What we're trying to find is something about the angle. And anytime we need to relate lengths to angles, that's a job for trigonometry. That's why trig was invented. So, the way we're going to proceed is by taking the sides that we know here and creating a ratio out of them. And there are a couple of possibilities. I could do 80 over x, or I could do x over 80. My favorite is to do the ratio that has the variable at the top, so I don't have to worry about using quotient rule. But there is no wrong choice here. I can do either one. Having identified a ratio, let's pick one. Actually, we'll consider the two possibilities. Here's one, here's two. 80 over x. Then I ask myself, what ratio is that? This is theta here, so 80 over x is the opposite over the adjacent, and opposite over adjacent is tangent. So 80 over x equals the tangent of theta. So we begin with the ratio, and then we identify that ratio using our good old SOHCAHTOA. If, on the other hand, I do x over 80, then x over 80 is adjacent over opposite. What is adjacent over opposite? Not secant. Cotangent. Right. So it may be that if I know all 6 trig ratios well, then that frees me up to choose the most convenient ratio. If I only know opposite over adjacent is tangent, then I'm stuck using opposite. So there's some virtue in knowing your 6 trig ratios, thinking through those, right? Let's take this one here. Does anybody have a question about how we identified our equation? Because this was the key point in this problem. This was our key move. Let's walk through them. Let's see here. What is secant in terms of opposite and adjacent hypotenuse? Hypotenuse over adjacent, very good. One over cosine. And what is cosecant? Hypotenuse over opposite, right? So sitting board in English class, you might want to think through those 6 sometime to make sure that you have those clear in your mind, because it's nice to have all 6 available to you so you're not stuck. Now that I have a relationship between them, I'm ready for a time derivative. Everybody take the time derivative of both sides. Go. Sure. This is correct. This is not. You want to think outside of this. So you can remove the outside. So you can say when you use chain rule, you always multiply. We're gonna ask that, we can answer that question. Good. So on this side, out comes the constant, and we get 1/80th dx dt, right? On this side, we get negative cosecant squared theta times the derivative of the inside, which is d theta dt. But now we have two important things. Thing one, our trig derivatives go all the way back to the limit of sine as theta goes to 0, sine theta over theta equals 1, etc., which is only valid when theta is measured in radians, not degrees, per Hsu textbook. So our first order of business is that we have to convert our rate of change from degrees into radians. This is only valid for radian angles. And so this means we need to do a quick change of d theta dt equals 0.27 degrees per minute into radians. What's my conversion factor for pi over 180? That's right. Pi radians is a half circle. 180 degrees is a half circle. And so I get 0.27 divided by 180 times pi. This calls for a little bit of calculator action. Which is 0.0047 radians per minute. So that's the first thing that was a little bit of a twist that they threw our way. The second thing is I now have to evaluate this cosecant theta. So how am I going to do that? Two possible options. One is to find theta first and then find its cosecant. And I would find it first by going back to here, plugging in the value of x is 60, doing an inverse cotangent, blah, blah, blah. However, that is not necessary. I can find the secant, or the cosecant of theta, without ever needing to find theta itself. How? Pythagorean theorem. Going back to our triangle right here, the cosecant of theta is equal to the hypotenuse over the adjacent. And I can find the hypotenuse of this triangle simply by using Pythagorean theorem. In fact, I don't even need to work too hard, because what special right triangle in disguise is this? It's 3, 4, 5. That's right. This is 3 times 20. This is 4 times 20. So this is 5 times 20, which is 100. Isn't that convenient? Therefore, the cosecant of theta is hypotenuse over adjacent, or 100 over 60, which is the same as 5 over 3. And now I have a value for cosecant without ever needing to find the angle itself. Moral of the story, if you have one trig function, you can find them all without needing to find the angle. Yes, ma'am. Is cosecant hypotenuse over opposite? Yes, yes it is. Thank you. I am so sorry. I'm tired too. Huh. Look at that. So hypotenuse over opposite. So that would be this, which reduces to 5/4. And back we go. Good catch, Bethany. And our d theta dt is still 0.0047 radians per minute. Okay, now what about units? Well, the units of the 80 are 80 feet, right? The units of feet here cancel, so we get a pure number for our trig functions. Trig functions are always pure numbers because they are ratios of one length over another length. And the units here are radians per minute. When I multiply feet by radians, oddly enough, I get feet. The radians are kind of like those units. And so the result is this guy right here, which I can simplify if I really want to, but I'm not sure that I want to. Yeah, I'm curious. I want to know the decimal approximation here. Times 80 times 25 divided by 16 gives me negative 0.5890 feet per minute. Just like that. You look perplexed. Finally, we want to answer the question. They asked a strange question. They asked it like this: at what rate is the shadow decreasing? And so to answer the question that was asked, we would say the shadow is decreasing by 0.5890 feet per minute. How come I don't include the negative sign in my answer? Right, that would be a weird double negative. The negative sign is included in the word decreasing. So what's the moral of this story? The moral of this story is that if we need to relate angles to sides, we use trig. Oh, times 5/4 squared. Right, so I actually forgot to change out my 5/4 right there. And then after this, I use the d theta dt that I got.
Is that like times?
Yes, times and times. Better? Good. Yes.
I just wanted to do the other way in there.
Got something else?
Yeah,
Okay.